Welcome back to The Deep Dive. Today, we're looking at something you interact with constantly, probably without even thinking about it, data centers. You stream some music, check your feed, send an email, maybe chat with an AI. All that happens because of these humming buildings full of computers. But here's the thing, and it's kind of crucial. Not all data centers are the same. Not even close, actually. Okay, let's unpack this. Our mission today is to really get into the weeds of digital infrastructure. We're comparing those, let's call them traditional data centers, with the new kids on the block, these super specialized facilities built just for artificial intelligence. We want to see what's really different inside, the hardware and what they're actually for, how they run day to day, where they're built, and the big one, what they cost to set up and keep going. I'm really curious myself about how different they truly are. This should give you some real insight into the tech that, runs pretty much everything now, from your streaming queue to the AI tools popping up everywhere. It's a huge shift happening, so let's get a handle on it. So let's start with the basics. The actual stuff inside. We talk about the cloud, but it's all physical hardware somewhere, right?
Absolutely. It's very physical.
And with AI taking off, are we just talking more servers, or is it more fundamental? Like, looking at the hardware, what's the first big difference you see between a traditional center and an AI one?
That's the perfect place to start, because the hardware difference is stark. It really sets the stage. So in your typical traditional data center, you're mainly looking at general purpose servers. Think of them as the reliable workhorses. They run on CPU central processing units. Basically, the computer's main brain, good for lots of different tasks, running software, basic math, that sort of thing. And alongside those CPUs, you've got tons of storage hard drives, SSDs holding, everything. Databases, websites, your emails, company files, you name it, built for versatility.
Right, handling lots of different jobs at once.
Exactly. Now, walk into an AI-focused data center, you'll still see some of those servers, sure. But the big difference, most of them are just absolutely packed, sometimes wall to wall with specialized chips.
Yeah.
GPUs are the most common graphics processing units.
Which aren't really for graphics here, right?
Not primarily, no. That's key. They, or things like Google's TPUs, tensor processing units, or other AI accelerators, are designed for doing tons and tons of calculations all at the same time. Parallel processing on a massive scale. AI models learn by crunching huge data sets, performing billions of operations simultaneously. It's like having an army of specialists tackling one giant math problem together. And the other thing you notice immediately, way more high-speed networking gear. Think of it like adding super fast multi-lane highways connecting all those specialist chips so they can talk and share data instantly.
So it's not just faster chips, it's faster connections between them too.
Crucial. Absolutely crucial for training these enormous models efficiently. What's fascinating here is how this fundamental shift, moving from general CPUs to these specialized accelerators, it basically dictates everything else. The power needs, the cooling, even how long the gear lasts. It's a completely different architectural philosophy.
Okay, so it's a ground-up redesign, almost, tailored for a specific kind of job, which logically means they're built for entirely different missions, doesn't it?
Precisely. Different hardware for different tasks.
So what are those tasks? What's the core purpose of each type?
Well, your traditional data center is there to run all the everyday business applications we just take for granted. Hosting websites, managing email systems, running those big company-wide ERP systems, enterprise resource planning, handling your online banking transactions, streaming video, doing backups. The list goes on.
The bread and butter of the internet, basically.
Pretty much. And the key thing is, the work is usually spread across many, many small independent jobs. Think of each server handling maybe hundreds of different user requests simultaneously. It's about breadth, handling lots of little things quickly.
Okay, makes sense. And the AI centers?
They're built for something much more focused and much more intense. Their main job, training huge AI models. We're talking about the large language models like ChatGPT, or those amazing image generation tools, or the recommendation engines that decide what you see on Netflix or TikTok.
The really heavy lifting stuff.
Exactly. And then, once those models are trained, the data centers also serve them up, making them available for you to use. But the defining workload is that training phase. It often involves just a few, but incredibly large compute-heavy jobs. These can run for hours, days, sometimes even weeks.
Weeks for one training run.
Oh yeah. consuming massive amounts of parallel processing power the entire time. It's about depth, sheer computational brute force for one enormous task.
Here's where it gets really interesting for me. That difference, lots of small jobs versus a few massive ones, that really paints a picture. It's not just more computing, it's a fundamentally different kind of computing.
Absolutely. The pattern is completely different.
And I've got to assume that translates into how these places actually run. The day-to-day operations must be worlds apart, right?
Yeah.
How does it impact things like power, cooling?
Oh, hugely. The operational demands are night and day, and frankly, this is where the costs really start to explode for AI. In a traditional setup, servers are humming along, dealing with that steady stream of small requests, so power use and cooling needs, they're relatively predictable, relatively stable, like a busy office building, consistent, but not usually extreme peaks.
And scaling up is probably more gradual?
Right. If a company needs more capacity, they often just add servers incrementally. A few more racks here, a few there. It's fairly linear.
Okay, now paint the picture for the AI center.
It's a different beast. Picture this. A single AI training job kicks off. Suddenly, hundreds, maybe thousands of GPUs spin up to maximum capacity all at once and stay there for days.
Wow.
Power draw is colossal. Think megawatts, like firing up a small town instantly. And all that electricity turns into heat. A lot of concentrated heat.
Which means standard air conditioning won't cut it.
Not even close. You need much more aggressive cooling. We're talking advanced stuff, like liquid cooling, where coolant flows right next to or even directly touches the chips to pull heat away efficiently. Or very sophisticated airflow management, like cold aisle containment to isolate the hot and cold air. The heat density is just too high otherwise.
And planning capacity must be different too. You can't just add one GPU at a time.
Exactly. It doesn't really work that way for efficient training. You need a large cluster of GPUs working together. So capacity planning happens in big chunks, deploying whole racks or even entire data halls full of accelerators all at once. It's much lumpier.
If we connect this to the bigger picture, that massive power draw, the intense, constant heat load, it's not just an operational headache, is it? It must fundamentally shape how these things are even designed and built.
It absolutely does. It's a core design constraint. It influences the building materials, the electrical substation requirements, the kind of power contracts they need, everything. It dictates the physical reality of the facility.
That makes perfect sense if you're generating that much heat and pulling that much power. But does that extreme cooling introduce new problems? Like, is it more complex or costly to maintain? Sounds fragile.
It definitely adds complexity, yes. Liquid cooling is efficient, but think about it. You've got plumbing, pumps, coolant, potential leaks, all running right next to incredibly expensive electronics.
Right. One leak could be disastrous.
Exactly. So you need specialized monitoring, specialized technicians. Maintenance is more involved and, yeah, more expensive. It's the price you pay for pushing performance to the absolute limit.
Fascinating trade-off. So given these very specific needs, especially the huge power and cooling, does that change where companies decide to build these AI powerhouses compared to traditional ones?
Oh, definitely. Location strategy gets really interesting for AI. Now, there's some overlap, of course. Both types, like places with relatively cheap land and reliable power, often suburban industrial parks or locations near major internet junctions for good network speed.
Standard data center stuff.
Right. But for AI-focused centers, there are extra critical factors. The biggest one, an almost desperate need for abundant, cheap electricity. We're talking locating right next to major power generation sources, massive hydro dams, huge wind farms, large solar installations, because the power consumption is just staggering. Tens, even hundreds of megawatts constantly.
Like powering a small city, you said.
Easily. So the cost and availability of power become paramount. It can be the single biggest factor in choosing a site. And the other big one, climate. Some of the big AI players are deliberately building data centers in colder regions. Think Scandinavia or the northern US, Canada.
Why? Just cheaper land?
Partially, maybe. But the main reason is cooling. They can use the outside cold air for free cooling for a significant part of the year. It drastically cuts down the energy needed for their artificial cooling systems, which, as we said, are a huge operational cost.
Wow, so AI data centers are literally chasing energy sources in cold weather. It really drives home the resource intensity, doesn't it?
It really does. It's a physical manifestation of the computational demand.
Okay, let's get to the brass tacks then. This all sounds incredibly expensive. What does it actually mean for the setup and running costs, the bottom line?
Yeah, the financial difference is significant. Let's break it down. Setup costs first.
For a traditional data center, maybe a decent-sized enterprise site with a few thousand servers, you're probably looking at tens of millions of dollars. Main costs are their racks, CPUs, storage, networking, power gear, cooling, and the building itself. A big investment, but somewhat standard.
Okay. And for AI?
Well, you start with the same basic building and power infrastructure costs, but then things escalate quickly. The specialized AI chips, those GPUs or TPUs, they cost way more per unit of compute than a standard CPU server.
Easily, several times more. A single high-end accelerator can be tens of thousands of dollars, and you need thousands of them. Then have the high-speed networking, that super-fast interconnect fabric like 200 gig Ethernet or NVLink. That's another major expense category. And the specialized cooling we talked about. Liquid cooling systems, big chilled water plants. They can easily double your HVAC budget compared to a traditional air-cooled setup.
Okay, so adding it all up.
Crucially, a comparable size AI facility can easily cost 2 to 4 times, maybe even more, than a traditional one to build. We're talking $100 million, $300 million.
Yeah.
For a large-scale site, it can definitely push into the high hundreds of millions or even billions.
Wow. Okay, that's a huge difference in upfront cost. What about running them?
That scales up too. Traditional centers have predictable power bills, moderate cooling costs, standard staffing for upkeep, security, networking. AI centers, the power draw is vastly higher. Remember, megawatts constantly. That translates into enormous electricity bills. Cooling becomes a massive operational expense, sometimes rivaling the cost of the power for the chips themselves.
And the staff need different skills.
Yeah, you need people who understand GPU health, specific AI monitoring tools, and frankly, you might be swapping hardware more often. Those GPUs running flat out 247 for training, they can wear out faster than CPUs in more varied workloads.
Which brings us to lifespan. Does the gear become obsolete faster too?
That's another huge factor. In a traditional center, you might refresh your servers every, say, 3 to 5 years. The building itself can be useful for 15 years or more. But in AI, the cutting edge moves so fast. A top-of-the-line GPU today might be significantly outperformed, almost obsolete for leading-edge training, in just 2 or 3 years.
2 or 3 years? That's incredibly fast.
It is. It means that compute layer, all those expensive accelerators, needs very frequent, very costly upgrades just to stay competitive, even if the building and power systems remain. This raises an important question, about the sheer pace of investment needed, the sustainability of constantly replacing hardware, and how it impacts innovation cycles. It's a treadmill.
So what does this all mean? If I'm trying to explain it simply, it sounds like an AI data center isn't just a tweaked version of the old model. It's like a completely different species.
That's a good way to put it.
More specialized, definitely more power hungry, generates way more heat, and is significantly more expensive to build and run. It's like comparing a reliable minivan to a Formula One car, right? Both have engines, but designed for vastly different things with vastly different costs and operating needs.
An excellent analogy. Built for pure performance on one specific demanding task.
So just to recap for everyone listening, we've seen today that AI data centers are these highly specialized beasts. They're fundamentally different from traditional ones in their core hardware, with all those GPUs, their purpose focused on massive training jobs, their intense operational needs for power and cooling, their location often dictated by energy sources, and yeah, significantly higher costs across the board.
Right. It's not just a minor upgrade. It's a whole different category of infrastructure.
And these differences, they aren't just technical details, are they? They have real impacts.
Absolutely. They have profound implications for you, for everyone. The apps you use, the online services, the AI tools becoming part of daily life, they rely on this rapidly evolving infrastructure. This evolution enables incredible innovation, sure, but it also demands staggering amounts of resources, energy, materials, specialized engineering talent, huge investment. It's reshaping our digital foundations and even influencing things like global energy grids and supply chains.
It really is a foundational shift, which leads to a final thought. Considering this incredible growth in specialized hardware, the massive energy needs, what's next? What kinds of innovations might we see, not just in AI algorithms, but in how we actually build, power, and cool these digital behemoths in the future? Will we need radical new energy solutions, completely novel cooling methods, a different way of thinking about where compute happens? It's definitely something for you to mull over until our next deep dive. Until next time, keep exploring, keep questioning, and keep diving deep. Thank you for listening to today's podcast. Please feel free to click on the link in the description below to discover more podcasts.